Hi guys. So I want this presentation or video to be a quick recap on recursion, which is quite a difficult topic that we did address very briefly last week. And I want this to be sort of like the cherry on the top for that lesson to help you clarify and sort of figure out how recursion works once and for all. Right. So recursion is defined as repeating something. But we've already done repetition in the form of a loop. So how exactly is recursion different? It's repeating a particular task by calling a function from within itself or in on itself. That is where you have a function and the same function is called within that function. That very function calls itself. And that's really what establishes recursion. And it is basically a type of loop, but it is not written in the conventional way or iterative way. It's written in a recursive way, which we'll look at in detail later on. So you can see this sort of Winnie the Pooh meme here, where on the top section, you see recursion without something called a base case, where recursion keeps on going forever, right? And as you can see, the top half of the meme is replicated in the meme itself. So you can see this sort of infinity window going in. That's sort of how recursion works. You might have seen this kind of thing with paintings where the painting inside it has the painting inside it again. So the painting is within itself and it sort of repeats to infinity. But technically, we don't want that infinity effect in computer science because that will have drastic consequences. We don't want to run out of memory. So instead, we have something called a base case, which sort of stops the repetition at a particular point or stops the recursion at a particular point. Hopefully that made sense. Now, we'll start off by understanding recursion by looking at a small problem. The problem is find the sum of the first n digits starting with 1. Right? So let's try solving this using a for loop in Python. And I'm pretty sure that you guys are already comfortable with writing for loops. So this shouldn't be too difficult for you to understand. We start off by asking the user to input a number, which we will consider as 4. And that value is saved into n. By the way, the current line of execution is shaded in red color, and the values associated with the execution is placed on the trace table on the right. So right now, n is 4. And then the total is set to 0, right? Which means that the total, of course, the question asks us to find the sum of the first 10 digits. Right now, we haven't added any of the digits, so it is 0 at the beginning. And then we establish a for loop that starts counting at 1 and stops counting at 4. Now, you might be wondering, if it stops counting at 4, why do we say n plus 1 as the stop value of the for loop? The reason is owing to how Python has its stop value exclusive, which means that if you want to stop counting at 4, you have to specify 1 more than that, or you have to specify 5 in this case. That is only when Python will stop counting at 4. So right now, the for loop starts at 1, goes on until 4, although we've specified 5. And then each time, the loop will iterate through, adding each new I value to total. So right now, I is 1. I gets added to total, which is initially 0, to increment it to 1. And then I becomes 2 as a result of the next for loop iteration. And then that 2 gets added to the current total, which is 1, which is 1 plus 2 becoming 3. The next iteration I becomes 3, 3 plus 3 is 6. The next iteration I becomes 4, 6 plus 4 is 10. And this concludes the loop. And of course, at the end, you get 10 and, the loop ends and the total is outputted as 10 on screen. So that wasn't too difficult. But now the problem is this is still repetition, but not in the form of a recursive function, or we've not done this in the form of recursion, right? How exactly do we do this using recursion? What exactly do we need to do differently? The idea is we start off by representing a problem like that mathematically. Now, at least at A levels, we can have fair confidence that the problems we get are mostly based on mathematics. So it's fairly simple. And by the way, these are problems pertaining to recursion. it'll be mathematical, but of course, other problems will mainly be non-mathematical. But problems pertaining to recursion might mostly be mathematical. But there might be certain scenarios such as binary trees that might employ recursion, and then merge sort that might employ recursion, that are not fairly mathematical in their sense, but computer science related. So for the purpose of this presentation, I'll stick to mathematical examples, but do know most of the question that you get in the exam for recursion might be mathematically based. And there might be a few scenarios like binary search or merge sort or binary trees that might employ recursion out of mathematics, but just a few examples, or just a few scenarios. So here we are trying to represent the problem of finding the sum of n digits starting with 1 mathematically. So in our for loop, what happens is in each iteration, we sort of add the current counter to a total, and that is sort of represented in this first sequence, 1 plus 2 plus 3 plus 4 plus 5, all the way until n minus 1 plus n. But what I want to do is I want to represent this the opposite way, starting off with n and ending with 1. Now, the reason I do this is because n is something that the user will input, which is something that can change. So rather than figuring out 1 to n, it's best if we start off with the user specified value and decrement to 1. So that way it's a little easier for us to work with it. Of course, no one's going to, punch you if you do it the first way. You can do it the first way. But for this question, I'll do it the second way, where you start at 1 and you sort of decrement all the way down to 1. Right? You start at n and you decrement all the way down to 1. So the idea is, once you've represented your problem mathematically, you would have to, rather than solving the problem at once, break it down recursively. That is, you find the sum using previous sums, right? Now, as you can see, if n is equal to 5, the current sum would be s base 5, which is just a mathematical representation of arithmetic summation, where you have 5 plus 4 plus 3 plus 2 plus 1. But rather than thinking about it as a sequence of this big sum of values, why don't we think about it recursively? That is, to think about it step by step. The sum of the first 5 natural numbers is basically 5 plus the sum of the first 4 natural numbers. And the sum of the first 4 natural numbers is the number 4 plus the sum of the first 3 natural numbers. So notice, you can see that rather than thinking about the entire sum as a whole, we've done 5 plus S4, then S4 is 4 plus S3, then S3 is 3 plus S2, S2 is 2 plus S1, then S1 is 1. So we sort of stop there, we sort of break the whole flow there, but we'll see why. But that is what it means to think recursively. Rather than thinking about this as a big fat sum, we think about it in parts. Now, we are going to investigate a few important terms that are associated with this recursive solution. We start off with a particular starting value. The starting value in this case is also the input value n, which the user will specify. Then we have an ending value. That is, we start at 5, and the last number we add would be 1. And then following that, we also have something called a base case. The base case, in this case, is 1 as well. And what base case means is, if you remember the Winnie the Pooh meme from the first slide, it's basically where you stop recursion, where you stop looping any further. Now, since we're starting at n and we are sort of going down by 1, we would stop going down further once the n value of the sum reaches 1. Not when the sum itself reaches 1, but when the n value of the sum reaches 1. That is why the ending value, I've labeled the 1 after the equal sign, but the base case I've labeled as the subscript of s, that is the current n value or the current sum we are working on. So that's the base case. When the sum n value reaches 1, we stop asking for further sums. And then our final output would be s base 5, that is, what is the sum of the first 5 natural numbers. This would also be considered as our return value. But this is not only our return value. there will be intermediate returns or intermediate outputs, which are basically returns that take place within the recursive function calls. Now, of course, these might not make a lot of sense to you right now, what these specific terms and returns mean, but we'll look at it briefly and probably more clearly as we move on. So if I backtrack a little bit, the idea is, if you can figure this part out, the part where you take a problem and you represent it recursively, you're basically 90% done with the problem. We're 90% done with the hard part. The remaining 10% is the easy part. So the idea is, you take a problem, you break it down, where you represent the problem using parts of the problem itself, sort of using sub-problems. So our problem is figuring out the sum of certain numbers. We represent that sum using the sum of its smaller numbers, its constituents. So S of 5 is represented as S of 4 plus 5. S of 4 is represented as S of 3 plus 4, and so on all the way until 1. Right? That's the idea. Now, how do we sort of program that? To program that, we need to first represent Sn in Python as a function. Here I will call S of n as, not S of n, S base n as total n, where n is a value that is taken in as a parameter. And we, at the end of the day, return S. Now, we'll get rid of return S soon, but this is just to show you that the function is called total. It takes in an n value, and it returns the final sum, whatever the sum may be. So this function is supposed to add up all the values from 1 to n and return S, which is the total of all the values from 1 to n. Now, what we do after this is you represent the base case as a condition within this function. So notice our base case was when the base of the sum is 1, or in other words, when n is 1, we stop asking, or we stop calculating further sums. That is exactly what I write as an if condition. We say if n is equal to 1, and we don't really worry about anything right now, but we just say return. Now, we'll see why we do return here soon, but for the moment, we'll just stick to the flow. If n is equal to 1, we'll do something. Otherwise, we'll do something else. So this is our base case when our recursive program should stop. Right? So our base case in this case is when n is equal to 1. Right? When n is equal to 1, we stop calculating further sums. The other case is, of course, the opposite of this is when n is greater than 1, assuming that n is a positive number. The recursive case is n greater than 1. So base case is when the recursion stops running. Recursive case is when the recursion keeps on going. So it's basically the opposite of the base case. So if you have the base case derived, you can basically figure out the recursive case from the given base case. The next part is establish the ending value as the base case's return. Now notice how I told you that the ending value and the base case are two different things. The base case is where n reaches 1. But when n reaches 1, the sum is 1. That is, the sum of n1 is 1. So then in that case, I will return 1. Now, it's the nature of this problem that results in both the base case and the ending value having a 1. But there are, of course, plenty more problems that have a different base case than the ending value. So don't get confused just because they are both 1s. Don't assume that they are both going to be the same. The ending value is what happens when the base case is reached. In this case, it would be 1. So I return 1 under the base case if condition. The next thing is, again, a pretty crucial component. Now, if you look at everything other than the base case, notice how I've cut off the base case with a line. Everything above that can be summarized to this yellow color formula, right? Where the S base n, that is the sum of a given n digits, can be represented as n plus the sum of n minus 1 digits. So everything above the base case can be sort of generalized to this expression. And once you sort of understand this generalization. All you have to do is sort of implement it in Python. And what that returns to, or what that sort of gives us, is n plus total n minus 1. So s to the base n equals n plus s to the base n minus 1 is rewritten as n plus s to the total, which is again similar to s, n minus 1. Right? So we took that same mathematical representation and we represent it in the computer. That's the idea, right? We present immediate returns as a recursive case return. So that's really what went on here, guys. So let's quickly recap. This is all we need to do for our recursive function. Let's see how we did this. We represent the solution starting from the input value. Rather than representing the sum of n digits as 1 plus 2 plus 3 plus 4 all the way until n or n minus 1 and then n, we represent it as n and n minus 1 and n minus 2 all the way from that to 3 to 1. Represent it the other way, starting from the input value. And then we represent the solution recursively. That is, rather than thinking about it as a big sum of values, we break it down and represent it as s base n equals n plus s base n minus 1. That is, for example, if you are calculating the sum of the first 5 digits, that is equal to 5 plus the sum of the first 4 digits. If you're trying to figure out the sum of the first 25th digits, 25 digits, you're trying to figure out the sum of the 25 digits, you might want to do 25 plus the sum of the first 24 digits, right? So for any given n, it can be represented as n plus n minus 1 sum. And then we represent the solution as a function. We represent s base n as total n, because we don't have subscript systems in Python. We just represent it as total, with the parameter being n. And then we represent the base case and the ending value. So the base case becomes our condition. The ending value becomes the return inside the base case. So n equals 1 becomes return 1. And then otherwise, you would do return n plus total n minus 1. That's the formula in step 2 represented in Python. We represent the recursive case with immediate value return, right? Intermediate value return, beg your pardon. That's where you return in case you haven't reached the base case. Now let's execute this. Let's see how exactly this happens. How exactly does this give us the final sum? Now, to achieve this, we have to call the function from the main program. If not, the function doesn't run. Just because it's recursive, it doesn't just start off running for no reason. It has to be called. So total, I'm going to call the function total from my main program with an n value of 4 initially. That's just a choice that I've made. You can choose a different n value. No harm in doing that. And notice how I've created another section called the call stack. The call stack will keep track of each function call. So right now, the red color highlight is over total 4, which means that that function is going to get called. And as soon as that function gets called, guys, do you see that that function and its respective value gets added or pushed to the call stack, right? So keep that in mind. And then we've moved on to the function's header. Right now, n is 4. Keep that in mind. We check if n is equal to 1. Not really, right? 4 is not equal to 1. So then we go on to the else, and then we perform the return. So what happens here? You say return n plus total n minus 1. What's n in this case? 4. What's n minus 1 in this case? 3. So return 4 plus total 3, right? That's what evaluates. But there's a small issue. Total n minus 3, and n minus 1 is 3, total 3 wouldn't give us the answer immediately, right? Total is another function call. So what happens is that portion of the function call is going to get added to the call stack once again on top of the total 4. So remember, 4 plus total 3 is appended, or in this case, using the proper terms, pushed into the stack with its respective values, because we don't know what total 3 is yet. It has to go on calling further and further to actually get to the result of whatever total 3 is. So that's the beauty of recursion. We forget about the answer momentarily until we figure out the last value. And only once we figure out the last value, we figure out the other answer. So it's sort of like the computer science appreciation of ignorance is bliss, where we forget about problems momentarily. Now, of course, we can't stop the program here. Total n minus 1 is called again. But now n is 3. Keep that in mind. N is 3. Is n equal to 1? No. And then what happens? You're going to call n plus total n minus 1 again. Now see what happens. N is 3, total n minus 1 is total 2, and that's going to get appended to the call stack once again. And then the function is going to get called again. Don't worry, this will come to an end. N is 2 equal to 1? No. And then you return 2 plus total 1, which is n and n minus 1. And then total 1 is called where n is now 1. Now, since n is 1, what happens? It's going to become true. Now we've reached the base case. And then it's going to return 1. Now notice, look at the topmost function call in the call stack. Currently it says 2 plus total 1 because total 1 hasn't been evaluated yet. But as soon as n hits 1, you're going to return 1, right? That's the importance of the return, guys. Without the return, the previous function calls don't get the values. So right now, when we return 1, only then would 1 sort of be evaluated as the answer for total 1. And then the final answer for this function call would be 3, 2 plus 1. And then what happens? Because of the return, that 3 is going to get passed back to the previous call stack function, which means it's going to get evaluated to 3 plus 3. And then notice how we are in this red color line where it says return n plus total n minus 1. That's where we left off in the previous function call, right? So that means in this function call, the final value is going to get evaluated as 3 plus 3, which is 6. And that is going to get returned to the previous function call, right? That's going to be 4 plus 6, the 6 from the function call that came just after it. Now it's returned to the previous one. So 4 plus 6 becomes 10. 10 is going to get returned to the last function call, which is the function call we made at the beginning. And 10 is at the main program level now. So see, it's very beautiful. You use a stack to keep on recursively calling a function. And then once you reach the base case, you stop and you immediately return the value. Keep on returning until you reach the main function call. You don't have to really call it in the main function. You could call it in any other function, but it sort of keeps backtracking until it reaches the very first function call. So right now the value is 10. That is correct. The sum of the first 4 digits is 10, right? 1 plus 2 plus 3 plus 4. Seems pretty interesting. Seems pretty counterintuitive, right? Now, a few key points. The process of recursively calling a function is called winding. When this happens, a new function call gets pushed into the call stack. So remember the word winding is pretty important for your exam's purpose. Winding is when you recursively call a function again and again and again, right? But then you will eventually reach the base case. Once the base case is reached, each function starts to get returned one by one. This is called unwinding. And when unwinding happens, each function call gets popped off the call stack. So when you push, you wind, and when you pop, you unwind. And those are a few terminology associated with recursive functions. And then this might be an interesting thing to look at. What happens if you don't have a base case? So again, looking at our first slide, that's what happens when Winnie the Pooh keeps on calling itself. Sort of Winnie the Pooh meme is within the Winnie the Pooh meme, and it goes on going forever. That's what happens. So the call stack will get pushed new function calls indefinitely, right? Forever, sort of. But of course, we don't have infinite memory to keep calling it indefinitely. So what will happen is the call stack will run out of space, and you will result, or you will get to a position called a stack overflow, right? In Python, you'll get an error called maximum recursion depth error. 1000 function calls is the max recursion depth for Python. But you can, of course, increase this by using the sys.set recursion limit. Within open brackets, you can specify whatever other value you want to sort of change the recursion depth. But do keep in mind, changing this might affect your program for the better or for the worse. If you increase it, usually what will happen is your call stack will be bigger, and your computer might crash by the time it realizes you have an error, right? So you don't want to increase it way too much. You might want to keep it at 1000 and see if your program is working efficiently, rather than actually increasing it to see if your program is working instead. Right. So hopefully that is clear to you, right? From this point on, I'm going to look at a few more problems. So if you're clear with recursion, you can stop watching the video here. But if you want to look at how recursion is applied for further problems, you can stick around and go through the rest. Right. So problem 2 is to find the factorial of n. So similar to what we did earlier, we represent the problem mathematically. N factorial is basically n times n minus 1 all the way until 3 times 2 times 1. That's the factorial of n. Basically, it's the multiplicative sum of sorts of all numbers from n to 1, right? Then we try to represent this problem recursively. Now let's take an example. Rather than thinking about n as n, we'll think and substitute 5 to n, where instead of recursively representing the factorial of n, we'll represent the factorial of 5. Normally, 5's factorial can be represented as 5 times 4 times 3 times 2 times 1. But if you represent this recursively, what do we need to do? We need to represent the factorial of 5 as something times the factorial of another. So if you want to pause now and sort of think about how you might solve this. But once again, you need to represent 5 factorial as something multiplied by the factorial of another. And then that should sort of continue all the way until you reach the base case. So pause the video now and figure out it by yourself. Right. So if you figure this out, you should probably have something like this, where 5 factorial can be represented as 5 into 4 factorial. 4 factorial can be represented as 4 into 3 factorial. 3 factorial can be represented as 3 into 2 factorial, and so on. And you stop doing this once you reach 0 factorial, which technically is defined to be 1, right? And we can generalize this as n factorial is equal to n factorial, n factorial is equal to n times n minus 1 factorial, right? So this is the hard part done now. If you were able to figure this out by yourself, give yourself a pat in the back. Well done. Now, we also need to identify one more thing. This is our base case. That is 0 factorial equals 1 is our base case. Specifically, when n reaches 0, that's our base case technically. We return 1. 1 is our ending value. Right. Let's now do the programming part. We represent the factorial problem as a function. We say def fact n return factorial, right? Of course, we'll get rid of factorial soon, but the word factorial is to represent the final answer we need. And then what do? We represent the base case and its respective return. So what do we do here? When n is equal to 0, we return 1. That is, when 0 factorial is what you achieve at the end, you will return 1 straight away because it's defined as 1. And then our recursive case return would be return n into factorial n minus 1. That is, n factorial is equal to n times n minus 1 factorial is represented in the computer as n into factorial n minus 1, where n minus 1 exclamation point represented in Python using the fact function is fact n minus 1. They are same thing represented in 2 different ways. And that's all. Nice. That's all we need to do for our factorial function. However, this function does assume that n is greater than or equal to 0, which is okay in a mathematical sense because we don't calculate factorials for negative numbers. Problem 3. Find the nth Fibonacci number. Now, we'll try and represent this problem mathematically by writing down the first few Fibonacci numbers. Basically, Fibonacci represented as capital F. The sequence is starting off at 0, then 1, then 1, then 2, 3, 5, 8, 13, 21. Basically, this sequence is formed by adding the previous two numbers that came before the current number. So the idea is any given term n is calculated by doing n minus 1 plus n minus 2, right? So the idea is if we were to represent that same idea, but as a formal representation, the third one in this sequence is calculated by doing the previous two numbers sum. So 1 plus 0 or 0 plus 1 gave you the third one in this sequence. The fourth 2 is achieved by doing the last two ones sum. That's 1 plus 1. The next 3 is achieved by doing 1 plus 2. That's the two terms that came before the 3. And this continues. Now you might notice that I've sort of grayed out the first 0 and the first 1. Now what that means is we need to explicitly specify the first two values of Fibonacci, without which we can't calculate the rest of the values. So you might be able to understand that this is sort of what will become our base case very soon, the 0 and the 1, because there's no other way to calculate the Fibonacci sequence's first two digits, because we need to explicitly specify them in order for us to figure out the remaining digits. Now, generally, we would sort of represent this as f to the base n, that is the nth Fibonacci number, is equal to n minus 1th Fibonacci number plus n minus 2th Fibonacci number, right? Fn is equal to fn minus 1 plus fn minus 2. So this is already represented recursively, right? Where you represent Fibonacci using a previous Fibonacci number. Now, as I said, these two will sort of become our base cases or ending values per se, the 0 and the 1. We'll see how that's implemented. So we would first write the Fibonacci number function. Here in this case, I've named it fib, which takes in a single parameter n, and it will return the nth Fibonacci number. That's the end goal. But I now then represented the base cases. The base cases being when n equals 0, we return n, we return 0 itself. When n equals 1, we return 1. Now, here's a small thing I want to tell you. In mathematics, when we calculate sequences, we start the sequences at first term, right? But here I'm starting at the 0th term. So in the computer, in this case, in this solution, the 0th term is equivalent to the first term in the Fibonacci sequence. So if you remember, it's 0, 1, 1, 2, and so on, right? 0 is the 0th term in this solution, but it is first term in mathematics. The first one is the second term in the Fibonacci sequence, but it is the first term in this solution. So F0, which is equivalent to the first term, is 0. The 0th Fibonacci number, or the first Fibonacci number in this case, is 0. And F1, the first Fibonacci number in this, or the second Fibonacci number in maths, is 1. So those two I define as separate base cases because they need to be explicitly defined. If n is equal to 1, I return 1. And if n is equal to 0, I return 0. And then coming to our recursive case, what do? We simply return fib of n minus 1 plus fib of n minus 2. That's basically what we represented in the equation, but in code. And here also, I assume that n is greater than or equal to 0. Right? That's it. Now, there are a few improvements I would like to add. Now, what if you don't want the maths implementation and the computer science implementation to be two different things? What if you want the sequence to start at 1? So then you can change the program as follows. You can figure out how this program works by yourself, but I've adjusted this to work for a sequence starting at 1 instead of 0. So the first term would be n equals 1, unlike n equals 0 earlier. So note that it assumes that n is greater than or equal to 1, unlike earlier, which assumes that n is greater than or equal to 0. And yeah, like I said, series starts at n equals 1. And this problem solution has only a single base case. So instead of taking two separate base cases, I've sort of combined them into single base case. You can figure out how that works as well. But that's it for recursion. Feel free to try this problem out with more mathematical problems. Try to represent them using recursive functions. And do get back to me if you have any questions whatsoever. Thanks, guys. See you next class. Bye-bye.